Today we are going to solve some problems. We are going to start from where we left in the last lecture. We will solve some problems on chords and then we will go on to the concepts of tangents and normals. Okay. So first question is, find the length of the focal chord of ellipse s equal to 0 which is inclined at an angle theta with major axis. So here, first we need to take an ellipse. Suppose let us say there is an ellipse here. Okay, there is an ellipse here and there is a focus. I am taking S as the focus. In most of the questions relating to the ellipse, when it comes to focal chord or any line passing through the focus, we generally take the right side focus, not the left side focus, because most of the time we are comfortable with that. Unless it is mentioned in the question, we do not do it otherwise. Okay. So we mostly take S dash, we don't generally take, we mostly take S, we don't generally take S dash. Okay. But it is, if it is mentioned in the question, we go for S also. So here this point is AE comma 0. You know the standard equation of ellipse, which is x square by a square plus y square by b square is equal to 1. Now we want to find the length of the focal chord of the ellipse which will pass through this focus, of course, but making an angle of theta with major axis, that is the important phrase. So suppose let us say there is one chord here and this is making an angle of theta. So how do we proceed with finding the length of the chord? What could be the best way? The best way could be to go for this idea. Suppose we know that this chord is passing through AE comma 0 and we know that the slope is going to be tan theta. So we can use parametric form and write the equation of this line in this way: AE plus r cos theta comma 0 plus r sin theta. So this becomes any point that is lying on this chord. Now if I substitute this in the equation of the ellipse, I can get some values of r because r is the parameter here. So this line is intersecting the ellipse at 2 points. Let us say for this, if we take this length as r1 and if we take this length as r2, we need the total length of the chord, that means we need r1 plus r2 in absolute form. Now that we will see after we get the equation. In general, when we proceed in this way, one of the r1 and r2 can be negative, but here we will take care of it after we simplify it. So let us say I substitute this in the equation. What do we get? Excuse me for a minute. So if we substitute it, what do we get? We get AE plus r cos theta by a whole square plus r square sin square theta by b square equal to 1. Now if I simplify this, what do I get? A square e square by a square plus r square cos square theta by a square plus 2aer cos theta by a square plus r square sin square theta by b square equal to 1. Now if I simplify this, what do I get? R square into cos square theta by a square plus sin square theta by b square plus first degree term, which is going to be 2ae cos theta by a square, and now the constant term. Constant term is going to be a square e square by a square. So a square will get cancelled and what is left here? 1 is left. So e square minus 1. Okay. So this is cancelled and we got e square minus 1. Now from here I can get r1 plus r2, that means sum of the roots, as minus 2ae cos theta by a square, and also I will get r1 into r2, which is the product of roots, as e square minus 1 divided by, okay, wait a minute. So, here also this coefficient must be there. So, here R1 plus R2 is equal to minus 2AE cos theta divided by A square into what is in the denominator, cos square theta by A square plus sin square theta by B square. Okay. So, we got this relation, and for the product of roots R1 R2 will be E square minus 1 by cos square theta by A square plus sin square theta by B square. Now, because we have applied the parametric form, now when we go in this direction we get R1, and when we go in this direction we get R2. So, algebraically one of these two will be having negative sign, and we are interested in the total length of the chord. If we do R1 plus R2, definitely we are not getting the length of the chord, because one of them is negative. So, absolutely it is not exactly the length of the chord. So, to get the length of the chord we need mod of R1 minus R2. Mod of R1 minus R2 is the length of the chord. So, for that what we need to do is we need to identify and calculate R1 minus R2 whole square. Now, what to identify here? We need to identify a formula which will fit best into this. So, R1 minus R2 whole square can be written as R1 plus R2 whole square minus 4 R1 R2. Okay. So, let us say we simplify it here. So, what do we get? We have to square this term. So, basically it becomes 4 e square a square cos square theta divided by a power 4 into cos square theta by a square plus sin square theta by b square, and also there will be a square on this. Okay. That is our R1 plus R2 whole square. Now, we need 4 into R1 R2 must be subtracted here. So, 4 into what is R1 R2? It is e square minus 1 divided by cos square theta by a square plus sin square theta by b square. So, here if you notice, we already got rid of whatever are the parameters that are available. So, this is in terms of theta, a, b and e. Once if we fix the ellipse, a and b are fixed, hence e is also fixed. Now, because this chord is having slope theta, theta is also fixed. So, effectively we got one constant which is in terms of only theta, a, b and e. So, this means we have actually finished the problem here, but we have to simplify it to close the problem. So, how do we simplify? So, here if you notice, one a square is getting cancelled. So, what are we left with? If I let us say take this 1 by cos square theta by a square plus sin square theta by b square whole square. If I take this common in the denominator, so what is left here? There is also 4 which is common. I can also take 4 as common. Okay. So, what is left here? E square into cos square theta by a square, this is left, and in this term what is left? E square minus 1 into cos square theta by a square plus sin square theta by b square, this term is left. Now, we know that in ellipse 1 minus e square is going to be b square by a square. So, here effectively including this minus sign, we can write this as b square by a square. So, then what happens? We can take some things common and try to simplify this. But there is e square here that can be balanced when we are taking this cos square theta by a square common. Okay. So, or in a way if I just take this term common here, so what do I get? Cos square theta by a square if I take this common. I will be getting E square minus E square plus 1. So, I hope you have noticed this. And also here when I write E square minus 1 as B square by A square, so the next term is going to be B square by A square into sin square theta by B square. Okay, so what is left here? We are getting E square cancelled, and here B square is also getting cancelled. So, we are basically getting cos square theta plus sin square theta by A square in the numerator. So, which will be 1 by A square. So, effectively the value is going to be 4 by A square into cos square theta by A square plus sin square theta by B square whole square. Okay. So, this should be the length of the chord that is required here. Okay. So, let me just check if we have done any mistakes here. Okay. So far good, we have just we have just solved it completely. Okay. So, now when it comes to finding the length of the chord with the angle theta, this is one way of solving it. The other way of solving it could be to go for the ideas of equation of chord in parametric form, then comparing the slopes with tan theta and then simplifying it, but that is going to be much longer way than this method. Okay. So, this is one way of solving it, and when it comes to any situation where a tangent or chord is already making an angle of theta with x axis, especially when it comes to chords, we prefer using this parametric form, which will make our algebra very simple. Okay. So, quickly make a note of this. And this page also. Okay. So, now can we proceed? Okay. So, next question. If exactly 3 distinct chords of ellipse passing through a comma 0 are bisected by this parabola, then there is a condition that we have to verify. So, here it says 3 distinct chords of the ellipse passing through a comma 0. So, what is a comma 0 here? A comma 0 happens to be one of the ends of the major axis. So, this is one end of the major axis, and passing through this, it says that there are 3 distinct chords. So, let me just analyze this geometrically. So, we have one parabola here which is y square equal to 4x. Let us say this is my parabola. Now, chords passing through the point a comma 0 are being bisected by this parabola. So, which means the midpoint of the chord must be lying on the parabola. So, what we try to do is we take one point on the parabola first, because this is midpoint of the chord. Using the concept of finding the equation of the chord through midpoint, we can find the equation of the line which is the chord. Then based on the equation, we will decide what to do to proceed. Okay. So, what do we see here? Let us say I take one point on this as 80 square comma 280, because in general any point like this lies on parabola. This is the parametric form of parabola. Now, what is the equation of chord if midpoint is given? It is S1 equal to S11. So, here when we apply this equation, we will get equation of chord. So, what will it be? X into 80 square divided by A square plus y into 280 by B square minus 1 is equal to 80 square whole square by A square plus 280 whole square by B square minus 1. Now, this 1 may get cancelled. So, now when I simplify this, I got an equation in terms of x and y and t. Now, how to proceed later? This chord must be passing through the one end of the major axis. That means, when I put a comma 0 in this chord, it must satisfy. So, let me just put a comma 0 and analyze what happens. So, when I put a here, I will get a square t square by a square plus this term becomes 0 is equal to a square t power 4 by a square plus here I am getting 4a square by b square into t square. Now, see if there are any terms which can get cancelled and simplify this into a polynomial. So, here luckily a square is getting cancelled, here also a square is getting cancelled and t square also is coming out to be common. So, when I take t square common and simplify the remaining terms, I will get, I am taking everything to RHS. So, from t power 4 t square is taken common, so t square is left. From here also t square is taken common and what are the terms that are left? 4a square by b square and here this, when this t square comes to the right side, we will get minus 1. Now, this is an equation which looks like a polynomial in terms of t. Now, in the question it claims that 3 distinct chords are possible such that they are bisected by this curve. That means, if we get 3 chords like that which are in green, so let us say there is one chord here and let us say there is another chord here which is actually the major axis itself. Okay. So, if we get 3 such chords, it means there should be 3 solutions of t, because there are 3 points of intersections on parabola, we should be getting 3 solutions for t. So, this equation of polynomial must be having 3 solutions for t, and we can see that t square equal to 0 is already one solution, that is going to give us the major axis as the chord which is being bisected. The other 2 solutions must come from the other part. Now, for this equation to get 2 solutions, this part which is t square plus something, this part must be negative for this part to have 2 solutions. So, that means 4a square by b square minus 1 must be negative, which means 4a square must be less than b square. Okay. So, this way we can solve this problem. Okay. So, I hope you have liked this solution. So, initially problem looks very big, but if we go systematically we can solve it very easily. Okay. Come on, take a note of this. Okay, next, if 2 distinct chords of x square by a square plus y square by b square equal to 2 through this point are bisected by another line, find the condition. So, here the analysis must be in the similar lines. So, what is given here? two distinct chords of this ellipse are being bisected by this line. So, that means the midpoint of the chords must be lying on this line. So, let us take any one point on this line. So, suppose let us say if I put x equal to t, y generally becomes b minus t. So, this can be any parametric point on this line. Okay. So, now taking this as midpoint, if I can get the equation of the chord and substitute this point there, then I should be getting two solutions for t. Okay. So, this is again in the similar lines. So, let us just solve it very quickly. So, meanwhile, if you think you are getting any plan and if you think you can execute it on your own, you can also pause the video, just pause it and then try to solve it. After solving, you can also look at the solution anyway. Okay. So, let us say I get the equation of the chord. So, it becomes S1 equal to S11. So, you know the idea, whenever we find the equation of the chord, this 1 is anyways getting cancelled. So, we can just write it without that 1. So, it becomes xt by a square plus y into b minus t by b square is equal to t square by a square, this is t square, plus b minus t whole square by b square. So, S1 equal to S11, we already cancelled minus 1 there. Now, this has to pass through that point a comma minus b. So, let me just put that. So, at by a square plus minus b into b minus t by b square, this must be equal to t square by a square plus, if I just open this, I will get b square plus t square minus 2tb divided by b square. So, now if I simplify this, I will get one quadratic equation in terms of t. Now, that equation must be having two solutions. So, hence discriminant of that equation must be greater than equal to 0. Now, applying this, I can get the required condition on a and b, whatever is required. Okay. So, how to proceed further? Let us take t square common. So, what do I get? I get 1 by a square plus 1 by b square. So, I am basically taking everything to RHS and simplifying. Now, when I take t common, in the right side I have minus 2b by b square, that is the only t term in the right side, and in the left side I have one t by a. So, when it comes to the right side, it becomes minus 1 by a, and similarly here I have minus into minus plus and I have t by b. So, when it comes to the right side, it becomes minus t by b. Okay. So, a comma minus b, that is right. So, so far this is right. Now, further, so when I take t common, it becomes 1 by b. Okay. So, that is fine. Next, the constant terms. What are the constant terms here? Here there is one constant term which is minus b square by b square, which will be minus 1. When it comes to the right hand side, it becomes plus 1. And there is one constant here which is b square by b square, which is also 1. So, this is my quadratic equation. Now, we need the discriminant to be non-negative. So, delta must be greater than equal to 0. So, what do we get from here? We are getting 2 by b, minus 2 by b here, here minus 1 by b. So, basically we are getting minus 3 by b. Is it right? So, I will just check this one more time. Okay. So, this seems fine. So, we are basically getting something like minus 3 by b minus 1 by a whole square minus 4 into 1 by a square plus 1 by b square into what is the constant term here? It is 2. This must be greater than equal to 0. So, if we simplify this further, we will get the required condition. Okay. So, let me just simplify this. So, we are basically getting 9 by b square plus 1 by a square, and because anyways this minus is getting cancelled because of the square. So, we will get plus 6 by AB, and next minus 4 by A square minus 4 by B square, and there is one 2 also extra. So, this 4 and 4 must be 8s. Okay. So, we have simplified all terms. Now, let us try to club all of them and try to factorize this if possible. So, here I am getting 1 by B square, and here I am getting minus 7 by A square, and here this is 6 by AB. This must be greater than equal to 0. So, this seems to be having easy factors. So, one factor is going to have 1 by B, other is also going to have 1 by B, and here we must be getting minus 7 by A square, and 6 can be written as 7 minus 1. So, we can just say that this is, let us say, plus 7 by A, and this is minus 1 by A. So, now see if you are getting the same thing or not. Okay. So, basically I have factorized it completely. So, further even if I take 1 by A common, so basically I can get a relation like 1 by A square into A by B minus 1 into A by B minus 7, A by B minus 1, A by B plus 7 greater than equal to 0. So, which means A by B must be belonging to either minus infinity to minus 7 or 1 to infinity. Okay. So, here if you notice, these negative values are not possible because A and B both are positive numbers. So, if I take ratio of A by B, these negative values must be avoided. So, which makes it that A by B must be always greater than equal to 1 for this to be valid, which is naturally correct for any ellipse. Okay. So, this way we can proceed for the problem solving. Okay. So, when it comes to ideas of any chords being bisected by any line or any curve, you know the method of solving. Okay. So, come on, quickly make a note of this also. This page also. Okay. Next. So, with this we completed all concepts of chords in very much details. So, when it comes to parabola, ellipse and hyperbola, what are the most confusing concepts? They are basically chords only. So, from advanced point of view, chords are very important, but from mains point of view, tangents are very important. But sometimes in advanced, tangents also can be mixed with chords, tangents also can be mixed with normals, it is perfectly possible. Okay. So, we have completed one segment which is the chords. Now, we are moving on to the tangents and normals. So, here I have mixed both concepts of tangents and normals together. So, whenever we are discussing a tangent, we are also discussing the normal. And there is also a direct pattern between tangent and normal. If you observe the pattern also, you can always understand how to use that pattern to remember equations. Okay. So, let us start with the first one. Suppose if there is an ellipse and there is a point on the ellipse, let us say x1 comma y1. Now, on this, at this point, if we want to find tangent, what could be the equation of the tangent? It is always s1 equal to 0. If the point is on the curve, s1 equal to 0 always gives tangent. You already know that. It is valid for all curves. May it be circle, ellipse, parabola, hyperbola, everywhere it is valid. And next, equation of tangent at P of theta, that means theta being the eccentric angle, what could be the equation? So, when I apply S1 equal to 0, what is the equation that I get? Xx1 by A square plus yy1 by B square equal to 1. Now, here in place of x1 and in place of y1, we can substitute A cos theta and B sin theta. So, if we do it, we will get the equation of tangent in parametric form, which is this form. Now, to find the equation of tangent, S1 equal to 0 is a standard formula that we can use for all second degree curves. But if it is not a second degree curve, you know what to do. You can differentiate, you can get the slope and you can find the equation of tangent. Okay. Can we move on to the next idea? Next, what could be the equation of normal at any point x1, y1? So, to understand this, let me just explain you this pattern. We know that here if you observe x into x1 by b square, x1 by a square plus y into y1 by b square is equal to 1. We know that this is the equation of tangent at the point x1 comma y1. Okay, this is the tangent. Now, to get normal, there is one simple pattern. But before that, let me explain this idea. If at any point, let us say if you differentiate the ellipse, if this is the ellipse, so you know this idea, but just I am explaining. So, the dy by dx is going to be, when we differentiate this, it is going to be minus b square by a square into x by y. This is going to be the derivative. So, this gives the slope of the tangent. Now, when we take minus 1 by m of this slope, we will get the slope of the normal. So, basically when we substitute the point, we will get the slope of the normal at that point. Okay. So, using that you can get the equation of normal, but that is a very long pattern, but there is one simple pattern. If you remember it, you can crack all normals. Okay. So, what you do is you just flip this number. Okay. So, if I flip this number, it becomes a square by x1. Again, you also flip this number. So, if I flip this number, I will get b square by y1 and there is y here. Now, flip the sign also, it becomes normal. Okay. So, we just have to flip these coefficients and flip the sign. So, this pattern is called as flipping pattern. So, if you remember flipping pattern, so you can easily remember the normal. Okay. So, now we here by doing this flipping, we will get only LHS. What about RHS? To get RHS, we have to substitute the point in this, because this has to pass through the point. So, if I just substitute the point, it has to satisfy. So, let us say if I put x1 here and y1 here, x1 and y1 get cancelled and what remains is basically a square minus b square. So, that becomes our RHS. So, using this pattern, we can remember normals. If we know tangents, we know normals. Okay. So, this is one idea of finding the normal at a point. So, look at the equation, it is exactly same. Now, let me explain it further, other case also, which is the parametric form. So, suppose we have already seen the parametric form here, which is x into cos theta by a, this is the coefficient, plus y into sin theta by b, that is the coefficient, equal to 1. This is our tangent. Now, what is the technique? Flip all of them. So, here it becomes a by cos theta into x, here it becomes b by sin theta into y, and now flip the sign. Now, to get the point, to get the RHS, put x as a cos theta, y as b sin theta, that will give us a square minus b square. Okay. So, here from this equation you can just flip it and get the normal, or if you know this equation, in this by substituting x1 as a cos theta, y1 as b sin theta, you can also get the equation of the normal. Okay. So, there are two ways of doing it, you can use whichever you want, but if you remember the pattern, you can remember the equations. Okay. So, I hope you have liked this pattern analysis. Okay. So, that way we can find the equations of normals. Now, when it comes to these equations, especially in the chapters parabola, ellipse and hyperbola, if you do not derive them on your own, you may not remember them. So, it is better that you derive them on your own only. Okay. So, next, if y equal to mx plus c is a tangent, of s equal to 0. Then what is the condition on C and M, or what could be the other situations? So, for that we can start like this. Suppose we have taken parametric form of tangent and we have taken this line y equal to mx plus c, and if we compare these two, because these two must be representing the tangent. So, comparing these two, we get cos theta by am and sin theta by minus b. So, here there is one extra minus sin theta here. Okay. So, sin theta by minus b, and that is equal to, if minus 1 comes this side, so it becomes minus 1 by c. So, from here if I simplify, I will get cos theta equal to minus am by c and sin theta equal to b by c. Now, if I eliminate theta from here, what do I get? If I eliminate theta, I will be getting something like minus am by c whole square plus b by c whole square is equal to 1. Now, if I simplify it, I will get c square as a square m square plus b square. Okay. So, this becomes condition for tangency. So, for any line y equal to mx plus c to be a tangent, this has to be valid. Now, is there any better method? Okay, this is of course the best method. Is there any other method which is not better than this, but is there any other method through which we can find the condition for tangency? Of course, there is one. For example, we have this line y equal to mx plus c, and we have this curve x square by a square plus y square by b square equal to 1. Now, if I substitute the line here and solve for x, then the number of solutions of x must be only 1 for the line to be a tangent. So, that means if I just substitute it here, I will just explain the method here. So, I will get mx plus c whole square by b square equal to 1. So, basically I am going to get one quadratic equation here in terms of x. Now, if this quadratic equation has two solutions in x, then it means the line is going to be a chord. If this quadratic equation has only one solution, that means real and equal roots, that means it is a tangent. If it has no solutions, line is nowhere related to ellipse. So, here we can just say that the discriminant must be 0 for the line to be a tangent. When we apply this and simplify, at the end we are going to get the same condition which we have just derived, but this is going to be very long. Okay. So, so if you want to avoid this long process, it is better that you learn this technique. Also, for normal, for condition for normal, we use the same analysis. So, this technique is better for normals also. Okay. So, now coming to this, if I put this condition in place of C, then that becomes naturally a equation of tangent in slope form. So, slope form of tangent can be written as y equal to mx plus minus whatever I am getting for C here, that I am writing. Okay. So, plus minus root of a square m square plus b square, it always becomes a tangent. Now, starting from this, because we got cos theta as this and sin theta as this, and we know that the point at which this line is a tangent is a cos theta comma b sin theta. So, we can find the point at which this line is tangent directly by using m and c. Okay. For example, here we got cos theta, a into cos theta will become minus a square m by c, and b into sin theta will become b square by c. So, this becomes our point where tangent is touching the ellipse. Okay. So, this way we can understand condition for tangency, slope form of tangent, and also the point at which it is tangent. Okay. Come on, make a note of this. Okay, next let us do the a simple discussion on this tangents. Suppose let us say there is one external point, this point could be internal also or it could be on the ellipse also, but let us discuss first for the external point. Point B, let us say x1 comma y1. Now through this point how many tangents are possible? 2 tangents are possible. Okay, so let us say this is the point. Now through this point 2 tangents are possible and we are interested in finding the equations of these both tangents. Then what is the best way? If the point is x1 comma y1, put this point directly in the earlier equation. Which is the equation? This equation. Put this point directly in the slope form and then solve for m. For example, here if I substitute x1 and y1 in that equation, so I will get this. Now in this what are the unknowns? If ellipse is given, a and b are constants. If point is given, x1 and y1 are constants. So what is variable here? M is the variable. So if I take mx1 this side and square this, I will get one quadratic equation in terms of m. Now if I solve this equation, I will be getting 2 roots for m. So it may depend, there are total 3 cases here. One case could be 2 roots, other case could be only 1 root and the next case could be no roots. So when we say no roots, basically we mean no real values of m. So when it comes to 2 roots, that means the point is outside and through that 2 tangents are possible. So if we put those values of m back in that equation, or if we use this point slope form of y minus y1 by x minus x1 equal to m, then we will get the equation of required tangents. Now but if there is only one root of this equation, it must mean that the point is already on the ellipse. If there are no roots, then that means it must mean that the point must be inside the ellipse. Okay. So this way we can analyze the nature of existence of tangents based on the location of the point. Okay. Or we can predict the location of the point using the existence of roots also. Okay. So generally this algorithm is used to find the tangents through any point which is generally outside. If it is on the ellipse, why do we have to go through so much struggle? We have S1 equal to 0. If it is inside the ellipse, of course tangents do not exist. Okay. So that is the main idea of this. Okay. So slopes of the tangents from this are roots of this equation, which is the result, which is the rule that we use to arrive at this result. Okay. So come on, make a note of this also. So now let us do similar analysis for normals also. Okay, so wait a minute. Okay, so let us say for normals also we want to do the same thing. Then we have this equation of normal in parametric form. Equation of normal is a square, it is not a square, it is ax by cos theta minus by by sin theta is equal to a square minus b square, right. Now if we try to compare this with this line y equal to mx plus c. So basically this can be written as mx minus y equal to minus c. Okay. Then what do we get? We get something like a by m cos theta is equal to here both are having minus sign. So b by sin theta is equal to a square minus b square by minus c. So from here we can get directly a relation between c, a, b and m. So how do we get that? If I let's say solve for cos theta here, so what do I get? I get minus AC by m into a square minus b square. Similarly, if I get sin theta here, sin theta can be written as minus bc by a square minus b square. Now we know that cos square plus sin square must be 1. So which will give us a square c square by m square into a square minus b square plus b square c square by a square minus b square. So this must be whole squared. Okay. So this must be equal to 1. So from this we can get relation for c, m and a. So what do we get from here? We get c square equal to a square minus b square whole square. Okay. So there is also m square here divided by, it is a square plus b square m square. So this is the condition for normal of line y equal to mx plus c. Now if we know the condition, if we put it back in this equation, we should be getting equation of the normal in slope form. So which means we can say that y equal to mx plus minus m into a square minus b square by, what is the denominator? Root of a square plus b square m square. So by doing this we can get equation of slope form of normal. Now if you try to compare this with the tangent, what is the difference? For tangent, this was the equation, y equal to mx plus minus root of a square m square plus b square. This was the equation for tangent. Now in comparison, you can notice that here what is happening? This m square is switching its side. M square, here it is coming with a square, here it is coming with b square, and here it is going up. Okay. So in the numerator we have this one extra term, because every normal has that a square minus b square term in the numerator. So this way we can understand and we can apply the connection between these two and try to remember it. Okay. So this normal can be also represented in slope form. If tangent can be represented in slope form, normal also can be represented in slope form. Suppose let us say there is one random point given. Through that point you want to find equations of normals. Now you do not know where that point is. If the point is on the ellipse, then it is easy, you can directly do it. But if the point is random, then how do we do that? Same analysis can be done. Put the point in this and solve for m. Whatever are the roots of m that you will get, you can put the values back and get the equations of normals. Okay. So let me just explain you that step also. Suppose if I put x1, y1 in this. So what do I get? y1 minus mx1 is equal to plus minus m into a square minus b square by root of a square plus b square m square. Now if I square it, what do I get? If I square it, I get y minus mx1 whole square is equal to m square into a square minus b square divided by a square plus b square m square. Now this LHS is already quadratic. In RHS also numerator is quadratic, denominator is also quadratic. So when I cross multiply here, I am going to get 1/4 degree equation in terms of m. So that means how many roots that this equation can have? It can have maximum of 4 real roots. So maximum of 4 real roots for m are possible. So this means through any random point, maximum of 4 normals can be drawn. Similarly, earlier if you observe for the tangents, because this is quadratic, through any point maximum of 2 tangents only can be drawn. But for normals, maximum of 4 normals can be drawn. Okay. So that is the conclusion of this idea. Okay. Maximum of 4 normals through any point can be drawn. Okay. So this point may vary. because every point need not have 4 normals. Okay. So, now that you have understood this entire analysis, let us look at the applications of these concepts and develop some more concepts based on the application and also solve some questions. Okay. So, now the application concept is the director circle. Now, what is the definition of director circle? Definition of director circle is, it is the locus of a point from which two perpendicular tangents can be drawn to any given curve. So, in our context it is the ellipse. Now, let us say if we define it in a different way, it is the locus of point of intersection of two mutually perpendicular tangents of the given curve. Okay. But in both ways you can also derive the equation in the same manner. So, how do we do this? To solve this, let us assume that the point is, locus point is h comma k. Let the locus point be h comma k. Now, through this point we could be able to draw two tangents and those two tangents must be perpendicular. So, what do? We just put this in the slope form of tangent, which is this. Okay. So, when we substitute the point in this, so what do we get? In place of y we will put k, in place of x we put h. So, we get root of a square m square plus b square here. Now, when we simplify this, what do we get? M square h square plus k square minus 2mhk equal to a square m square plus b square. Okay. Now, when I take m square common, so I will get h square minus a square minus 2mhk. There is only one term with the linear term. There are two terms with degree 2. So, we clubbed all of them, and then the constant terms, which is k square and minus b square. So, we just clubbed them also. Now, because these two lines must be perpendicular, m1 m2 must be equal to minus 1. So, m1 m2 equal to minus 1, this would imply that k square minus b square by h square minus a square must be equal to minus 1. Now, if we simplify this, what do we get? H square minus a square plus k square minus b square is equal to 0, which is same as h square plus k square is equal to a square plus b square. Now, at the end what do? Replace h with x, k with y. So, here that is exactly the analysis that we have done. So, because two tangents are intersecting at 90 degrees, m1 m2 must be equal to minus 1. So, that means this product of roots must be equal to minus 1, which would give us this. So, that becomes the equation of director circle, which is x square plus y square is always equal to a square plus b square. Okay. So, this way we can always find equation of director circle. Now, let us try to use our observations here. Suppose if there is an ellipse. Okay. Now, this has minor axis, semi-minor axis as B and major axis as A. Now, what is the radius? How is the radius behaving? If this is A, this is B, what is the radius here? R square is equal to A square plus B square. So, that means by if we form a rectangle here, this is the diagonal which is of this length. So, basically the circle is going to have this much radius. Okay. And of course, it will be concentric with the ellipse and also the eccentric circle. For both it is a concentric. Okay. So, that way we can understand the basic idea of this director circle. Now, to arrive at the equation of director circle, you can also use the concept of pair of tangents. For example, let us say you start with this idea, SS11 equal to S1 square. What does this give you? This gives you pair of tangents through any external point. Now, take the locus point as h comma k, through that point get the pair of tangents. Now, that equation will be of second degree equation because it is equation of POSL. Now, in that Because the lines must be perpendicular, put coefficient of x square plus coefficient of y square equal to 0. That will give you the required equation of director circle. You can also do it this way, but this method is faster. So, that is exactly why we learn the slope form of tangent and normal, because this way we can solve questions faster. Okay. Can we proceed now? So, please make a note of this. Okay. Also this page. Okay. Can we proceed now? These are some properties of tangents. Okay. So, let us look at the properties one by one. Here there is S, point S and point S dash are the foci and P is any point on the ellipse. Then the normal at P bisects the angle SP S dash. So, this means suppose let us say there is one ellipse here. There is one ellipse here and there are 2 points here which are the foci S and S dash. Okay. And P is any point on the ellipse. Now, we have one normal here. Let us say this is the normal. Now, normal must be always perpendicular to the tangent, of course. So, we have to prove that these two angles are always equal. We have to prove that these two angles are always equal. So, what could be the best way to prove this? Now, one idea could be this. So, basically I am discussing the ideas first and I will use only the idea that is easier for solving. Okay. So, idea 1 could be this. You can prove that angle between this tangent and this line, okay, of course it is going to be long. So, let us say this is alpha and this is alpha. You can prove that this angle and that angle are equal, but this is going to be very long. Whenever we want to prove that any line is an angle bisector, then we definitely do not want to go for this idea of incident angle equal to reflected angle or something. We do not want to do that. Then what could be the other method? Other method could be this. We can prove that the reflection of S dash is going to lie on that line. Okay. That means, if I see, of course, reflection of S dash about the normal is not S, of course it is not, but if we extend this line, this is going to be lying on this line only. Okay. Because we know that in angle bisectors, basically angle bisector is the symmetric line between these two lines. So, even if I am forming a triangle here, the reflection of this vertex must be lying on the other line. Okay. So, this must be satisfied. So, that is exactly what I was saying here. So, idea 2 could be that we can prove that reflection of one focus lies on the other line which is joining the point and the focus. But here again we need to use the equation of normal. Of course, we can use the equation directly, but we may have to find the equation of PS, that is going to take even longer time. Okay. So, idea 2 is better than the idea 1, but when required we can use it later on in some problems, but in this situation it is not required. There is a much better property. What is it? Angle bisector always divides the opposite side in the ratio of the other sides. We remember this property. So, we just get this point of intersection of normal with the major axis and then we compare this ratio, because we already know these focal distances. Okay. This is my idea number 3. We already know these focal distances. What is PS? We know that if I let us say take this point as A cos theta comma B sin theta, then PS is going to be A into 1 minus E cos theta, and PS dash is going to be A into 1 plus E cos theta. Now we just have to prove that this point P dash will divide the S and S dash in the ratio of the other sides. So that means we have to prove that P dash S by P dash S dash is going to be 1 minus E cos theta by 1 plus E cos theta. We just have to prove this. Now how do we prove this? Get the equation of normal and then get the point P dash. So what is the equation of normal here? Equation of normal is Ax by cos theta minus By by sin theta is equal to A square minus B square. This is the equation of the normal. Now I want to find the point where it cuts x axis. So just put y equal to 0 and solve for x. So here x will become equal to A square minus B square into cos theta by A. Now we know that B square is going to be A square minus A square into E square. So what is A square minus B square? It is basically A square E square. So here we are basically getting A into E square cos theta. This is the point P dash. P dash is going to be AE square cos theta, comma 0. What about S? S is going to be AE comma 0. What about S dash? S dash is going to be minus AE comma 0. Now find this distance. Distance between these 2 points is basically mod of x1 minus x2, because we know that this is lying in the right side, because here diagrammatically you can observe that. So we can directly get P dash S as AE common 1 minus E cos theta, and similarly we can get this distance. So P dash S dash is going to be, if I take this common, so what do I get? AE common E cos theta plus 1. Now what is the ratio of these two? We are getting 1 minus E cos theta by 1 plus E cos theta, which is the required relation. So we have basically proved that the normal bisects the PS and PS dash. Okay, so normal basically is bisecting the angle there. Okay, so normal at P bisects angle SP S dash. We have proved it using simple geometry. Okay, so I hope you have liked this technique. Okay, come on, make a note of this. This page also. So we will do the reflection property in the next lecture. We will stop today's lecture at this point. We will meet again in the next lecture with few more properties and problem solving. Until then, have a great learning day. Learning shall never stop.